recording. So I was gonna, as I was saying before, that so were you here last Wednesday?
I was.
Yes.
I missed Monday.
Okay.
That's what.
Last Wednesday when Kelsey was here.
Yes.
We did. I just found out that was basically all the homework. Like we just kind of went through all the homework.
Okay.
So, I mean, then there's a quiz next week.
Mm-hmm.
But we do have 3 more office hours before that.
Yeah. Okay. Your Saturday. Good.
So Saturday, yeah.
Good.
So, I mean, we could do whatever, but I don't know how much preparation everyone needs for the quiz. Beyond, because this homework I think was easier than the other homeworks. I think.
Okay.
At least doing it I didn't do all the problems, but I walked through it and they were like kind of involved 1 step each. So I assume the quiz give you this to like prepare for the quiz. So anyway, I could talk about whatever, or I could talk. So tomorrow I will be, as far as I know, I'll be teaching.
Okay.
And it's a new thing. It's chapter 12, which is not on the quiz. So I could start talking about that. I don't know if that makes everyone excited or upset.
This is when you need a poll.
I do need a poll.
The class.
Yeah. Well, you're the class now.
It's just getting very small.
Because the point is that if you want to not even think about it until after the quiz, that's sort of too bad.
Yeah, I know.
Because I have to teach it tomorrow.
Mm-hmm.
So, I mean, I guess this is not the best place to introduce it because not everyone's going to watch this. So maybe I shouldn't talk about it today. But anyway, the point is I don't know what to do today. That's what I'm trying to say. So just tell me whatever. The thing is, also, the other thing I was going to say is that all the quantum problems that could possibly help you, I think, with the quiz, I've done in the office hours before.
Okay.
So, like, I don't think it would be helpful for me to, like, make up another problem. I mean, again, I'm happy to do it if you want, but I just think, like, he's not, like, I could do a harder one, but then he's not going to give you that one. Like, he's probably going to give you the infinite square one.
You're probably going to go over it on Saturday anyways.
Yeah,
and I will probably go over on Saturday anyway.
Okay.
Then there's the shells, the atomic shells, which I could talk about as well, but a lot of people know them from chemistry classes.
Yeah.
And I don't think it's more in-depth than that. And the quantum numbers are just the L and the M are just the one that's just the D or the P or the S.
Oh, yeah.
Sorry, I'm saying a lot of letters. You know what I mean? The
SPD,
SPD, yes. SP, the F are the L's. Right, this is L equals 0, 1, 2, 3, and then the M goes from 0 here, and then it's plus or minus 1 or 0 here, and then it's plus or minus 2, plus or minus 1 or 0, etc. And that's how you count how many are in each shell and each. I guess I am talking about it now. But that's how big the periodic table is for each like block. Like the D block has let's see, 1, 2, 3, 4, 5 times 2 because each one of these has 2. That's 10.
Mm-hmm.
So the D block is 10 elements like wide. The P block should be 6.
Yep.
So you have 1, 2, 3 times 2 for each of these states. Well, anyway, whatever. So, you know what I mean. So I think that's kind of all you need to know for the whole periodic table thing. That was on the homework too. I think you need to like fill in that atomic orbitals or whatever.
Yeah, it's 10, 7.
Yeah, where you had to put like.
Predict the occupancy of 5 D-state transition metals.
Yes, and then you had to.
Hund's law.
Whatever to do it. Hund's law, right, which is the rule that tells you how to fill them in.
Yeah.
Where you write, 1s, 2s, 2p, 3s, 3p, 3d, 4s, etc., and you go like this.
Mm-hmm. Yep. You're good.
Right? So this is not, you sort of can't, well, I don't know where this comes from. I mean, I obviously it comes from real life, that's where it's from. But I don't know what mathematical rule that we know of that tells you that you go this way. Maybe there's something, we haven't learned it, and it's probably really complicated. It's probably some really subtle quantum mechanics thing. So, because you might think, why don't we just go in order this way? And I sort of don't know the answer. So anyway, but this is just Hund's rule or whatever. Is that how you spell it?
I think it's DS.
Oh, Hund. That's right.
I'm just.
Hund. I remember because it's a German person.
Mm-hmm.
I think it means hound, right? In German, or dog or something. Anyway,
Looks like it.
so that's the Hund's rule is that you go this way. And so the first two have one each, which really means 2 electrons each. And the second, that's why the periodic table has like the rows come in sets of 2 kind of thing. Like it's 2, except for the first one. Oh wait, no, yeah, hydrogen and helium have 1. Then you have, okay, let me just, this is a good thing to go over. Let me just commit to it instead of pretending to talk about it. So it looks kind of like this. And then over here, it's not to scale. Okay, then you have
Oh, no, you
1, 2, 3, 4, 5, 6.
oh, no.
There's 6, yeah. Okay, and then, okay, this is fine. Just pretend this works. So, and then there's 10 here. So the first sort of thing you fill in is the hydrogen and the helium. And there's 2 because each thing we go through on here is 2 electrons. So this is 2, and the second one we fill in is going to be the 2s states. So that's lithium and beryllium. So this is the 2s. So this again is one state which has 2 electrons. And then the next one we go through is the 2p, which is those are 6 here because this p has 3 states in it, which means, 3, quantum states, which means it has 6 electrons that go in it. So that's 6 here. The next one is 3s, which is these 3. So you can see that even though we're going in this diagonal thing, the row still corresponds to the n. Right, so the 3s is going to be these 2. 3p is going to be, I meant to do that. Yeah. And then this is 3s is here, and I don't remember what these are, magnesium and calcium, I don't know, whatever. What's this one?
It should be magnesium and calcium. Calcium is a 2
Are you sure
plus.
magnesium is +1?
I don't know.
I
I
thought
think
it was-
calcium was +2 charge though.
Oh, I used to remember these.
Yeah, me too. It's been a minute.
The alkali. Whatever, it doesn't matter. So there's things here, and then there's 6 here, because that's a 3p. Then the next one is going to be, then it's 4s, which is going to be these 2. So this is n equals 4. That's these 2. And then there's going to be a bunch here, and this is going to be 10 wide. This is going to be 10 wide, because this is the D block, because we're now at 3D. So that's this one. And then after this, we go to 4p, which is these ones, because n equals 4 in the p block, etc. And then the f block is the one that kind of has to stick out the bottom, because it has, how many does it have? Well, it has ±3, ±2, ±1, 0. So that's 1, 2, 3, 4, 5, 6, 7 times 2 is 14. So it's 14 states in the p block, 14 elements in the p block. Yeah. So the periodic table literally is in order if you follow Hund's rule and you want to organize it, because you can't just list them in order. You actually want them to sort of line up such that the columns correspond to things where there's a full state with 1 more electron, and the right side corresponds to the column corresponds to, if you want the columns to kind of line up as things with the same number of like outer electrons in its valence, the shells or whatever, then to follow Hund's rule, you kind of have to like split it up in this weird way. But now each block actually does correspond to one of these columns, and each row corresponds to the n value, which is the rows here. So it's sort of a weird, like the reason it's not like a perfect grid or something like that, or a nice little thing, is because you have to go diagonally here. So anyway, that's the Hund's rule. So if they ask you to fill in the things, fill in the electrons for a given element, they might tell you how many there are. You just know that, if they give you, I don't know if they'll give it to you if you have to write it out, but this might be like the 1s. And you're supposed to, this how you're supposed to draw them is like, you put 1s and you write the 2 electrons up and down, and then the next one is going to be 2s, and you write up and down, and the next one, you literally just follow this. Don't think about the periodic table when you do this, because it will confuse you. Actually, well, okay, that's fine. And then 2p, and then you can fill these in, and of course, it depends on the element you're doing. So I've done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've done at least to neon or whatever that is. Is that 10? Neon? I think it is.
Or, yeah. It is.
And so if they tell you, whatever the one after neon is, then of course the next one you would write would be 3s, and you just put 1 up in it, or down, doesn't matter. If you put down, it's not wrong, because whatever. But so that's it. And of course, the hard part about this is if they don't give you the boxes, which they probably won't, you have to know how big to put each. How did I know to make of course the S's, is just 1 box. But how did I know to make 3 in the P's? Of course, when I drive them, I counted, but let's just go back through to make sure we remember how to do it, which is that they actually sometimes call this M sub L. So I'll talk here, so the quantum numbers, I'll just write them all at once. There's quantum numbers for, I'll really write it, it's for V equals 1 over R, or minus 1 over R. All this means is V equals 1 over R is for elements. This is for hydrogen, really.
Mm-hmm.
So all the elements we're approximating as hydrogen, and that's actually a really good approximation. So the quantum numbers for this, of course, we've learned a lot about quantum numbers. There's in the infinite square rule, which is the other big example that we learned about. There's quantum numbers for X, Y, and Z and stuff like that. They don't always, of course, separate, as we've seen here. They don't separate into coordinates very easily. In this case, they kind of do, because the n, as we've seen, is the only one that matters with the radius. Like the shells are only like sort of stacked in terms of the radius, in terms of the n value, the n equals 1, 2, 3, etc. And we know that because the reason we know that is because if the energy is dependent on the radius, the average radius, then whatever this number is, I forgot what this number is. There's a number here, and then it's n squared. What is it, 16? No. 13, no, 13.6. This is the energy for the states as a function of n. You could even write n, L, m if you want, but of course L and m have no dependence here. So again, just to review what we're actually doing, it's not like, so, okay. What I'm thinking is that let's start over. We've done quantum mechanics problems where we start with a potential and we get some quantum numbers and some states and then some energies. And then we do this thing that seems like, oh, we're doing chemistry now. And I think what I really want to emphasize, which you probably already figured out by now, but just in case, what I want to emphasize is that this is not anything different at all. You just happen to learn this first because high school makes the state of, well, I guess we're not in New York, state of Massachusetts or whatever, wherever you're from, makes you learn this first. But it's actually a quantum mechanics problem where the potential is this instead of like a square or whatever we have, or like a cube or whatever. It's just this, and we get quantum numbers, so therefore we get states, psi, 3 quantum numbers, NLM, and we get energies, and it just happens that it's hard to solve them. That's the only reason we haven't done the whole problem out, is because it's very difficult. But we get states and energies just like every quantum mechanics problem. This is how it works. It happens to be that the energies only depend on n, which means it kind of tells us that there's something about n is sort of related to r. I'll put this in quotes because this is not like a mathematical statement. This is just saying that n and r are clearly related. In other words, if the energy only depends on n, and if the potential here only depends on r, well then clearly I can't have anything with L and M matter for clearly the only thing that changes your energy in this potential is being closer or farther. That's what R means. Being at a different angle or whatever, which is like, let's say we're in spherical coordinates, being at different angles clearly don't affect this at all. Only thing that matters is being closer or farther, the radius. And therefore, your energy, if it's only dependent on n, that kind of means that n is the only thing that n and r are sort of, n is the quantum number for how far you are, kind of thing. And we know that's true because we know in these shells that the higher n's are just bigger shells, right? They're literally farther away. As we've seen, and as you've seen in the diagrams, and of course, I'm sure a lot of you know this from chemistry, the other quantum numbers tell you about the shapes, and they have these like weird things like this, and they look like that, or whatever. Now that's fine, but and of course you can talk about distances, and maybe they stick out from each other, and if you map them out, it would look weird if you map them all on top of each other. But really, what we're talking about with the ends is the average distance. So even if they look weird like this, you still have an average distance that is the n value. So I guess I think we were talking about like when they bond, different electrons are more likely to bond because they tend to stick farther out. But if as long as in this approximation at least, and maybe the corrections are because not every element is exactly like this and not exactly hydrogen, but if we're being roughly, if that's roughly the case, the average distance that the electrons are at from the center is only given by that value, which only depends on n. So even if the S1 is a sphere, like the S1 is like a sphere this big, and the P1 is like a weird flower thing this big, and the D1 might be like even crazy with a donut or I don't know, whatever. If you just take the average distance they are, so they have all these probability distributions that are very important, and you could solve them, and they depend on L and M, but the average distance is going to be just depending on n.
Average of all the states, not just
Average of all the places it could be. So what?
S, P, D, F, all
No, it would just be yes, but like for example, for n equals 1,
Yep.
there's only an s.
Got
So,
it.
so yes, yes, but they might not have all those. Is how I'd answer it.
Thank you. Okay.
Yeah. So for example, the 4, if n equals 4, I could find already. You don't even have to tell me anything else. I could find the energy because that's all I need. But if I actually had to draw them, which you won't need to do because it's really hard. But if you had to draw them, the S, this would be 4S, would be like a sphere. This is obviously in 3 dimensions, but this would be like a sphere. The P would, and I'm making these up now because I don't really know, but they'd be like this weird thing. And maybe they'd have like,
Accurate.
is that right?
Yeah.
Okay. And then the D, so this would be 4P. And then 4D would, I don't know. There's like a donut. I remember that. I like the donut because it's kind of funny. There's like a weird donut thing, and then there's like, I don't know, or no, there's like another donut on top, and then on the, anyway, it's really, there's all these really weird, and it's actually not just this, it's actually this like, plus a bunch of other states added together or something. Anyway, the point is that if you say, and then because it's 4, there's up to F, so there's an F1, which is even crazier. But if you just take the average distance of all of those, they will all be only, I mean, you could literally just plug in n equals 4, compute this, and then plug it in here and find the R that it has to be at, right? Because if the only, so
V is the potential.
V is the potential.
Thank you.
And if I told you the potential, everything else in the Schrodinger equation is just for free particles. So this is the only thing that, it's just like potential energy. When we do potential energy problems, we convert kinetic energy to potential. There's no other place for the energy to be. It has to be in kinetic or potential.
Right.
So if I know n equals 4 and I know therefore I know the energy, therefore I can just compute the distance because that's the only place the energy is. There's no, we don't worry about kinetic energy. They're all just sort of,
Yeah, so -1 over that energy. You got it, right?
Exactly. Yeah, you could. Right. Exactly. So you
1,
could.
okay.
That's actually the reason I had a minus sign here is because I knew I had a minus sign here. So otherwise it would be like we could get negative values of the energy, which wouldn't be true.
Got it. Okay.
Well, I mean, we do get a negative here. I just mean this is a positive number because it's squared. Anyway, you'll see. Positive. Sorry.
You can't have a negative.
Positive. You can't have a negative
Yes.
R. Yes. Exactly. That's what I meant. Yeah. Now, I don't think you'd ever have to. I guess it could be a problem. It would be kind of a weird problem. But if they told you, like, in the n equals 4 state, how far away is the. I guess they could ask you that, and you would just have to know that you plug in 4 here, you get E, and then all of the energy is potential energy. And I guess a way you can figure out why it's all potential energy is because what's the average velocity of an electron here? Well, clearly it's 0 because it's not moving. Like, the fact that the electron can be here or here doesn't matter because the average position is the center, right? I mean, take an easy example would be just the S states, which are spheres. What's the average velocity of a particle that can be anywhere in a sphere? Well, it's just wherever the center. How fast is the center of the sphere moving? Well, it's not moving because it's at the center. So, yeah. Anyway, so you can kind of imagine by symmetry, it can't possibly be any other place in the center. Anyway, so that's the n quantum number, and then because of the Schrodinger equation in spherical coordinates, which is the really complicated equation that was in the slides, because it's like you don't. I'm not gonna write it. It's really hard, but you have to do this thing in the Laplacian exactly. If you do it in spherical coordinates, which are called r theta phi, and I'll just show you quickly what they are, just so you have an idea, because you should have a rough idea what they are. I think I talked about them a little last semester, but spherical coordinates are just like x, y, z, but instead of using x, y, z, you use r, which is so x, y, z. You have to have an origin, right? Because otherwise, what does it mean to be 5 meters in the x direction, right? There's an origin. The same exact thing sorry, let me keep going with that. In the XYZ frame, coordinate system, I should say, you have an origin and you have an orientation. So you have to know, A, where the origin is, but B, where X, Y, and Z are. Because, of course, if you just rotate it, you'll mess up all your... you have to know the orientation. So that's called, like, your frame, as you could call it. So what's your frame in spherical coordinates? Well, you have to have an origin. So if you're talking about a point, let's say a point is here. Okay, let's say you're talking about this point, you want to say the coordinates. Your first coordinate is called r, which is your distance from the center, r. And that's, it's literally just the actual distance from the center. Theta is going to be so it's obviously hard to draw in 3 dimensions, or to draw a 3-dimensional thing in 2 dimensions, but theta is going to be like I talked about this, the latitude and longitude. Theta and phi are latitude and longitude. So theta is at the top, you say this is theta equals 0, and then as you go down to the equator and then to the South Pole, you get theta increasing. So a point that's right in this, a point that's like in this plane here. Okay, a point that's like, so here you have a globe, a point that's straight, flat, in the flat plane that the equator goes through is at theta equals 90 degrees, and a point that's directly downward is theta equals 180, or pi. And then phi would be just the angle around that you have to go. So that'd be the longitude. So that's literally how you talk about, I guess, stars, I think. That's just a stupid example because the Earth moves. But how you talk about places on the Earth. Of course, you don't normally need to say R, because if you know the place, then you could just look at a map of, there's references of just where the elevation of every place on the Earth. But I guess if you're talking about an airplane, right? On an airplane, you might want to say, what position are you at? R is going to be your distance from the center of the Earth. Again, you wouldn't say it like that, but let's say you were. The distance from the center of the Earth. Theta would be your latitude, and then phi would be your longitude. So it's still 3 coordinates. You still have, because we're in 3 dimensions, you have to give 3 coordinates. There's no system you can make that has less than 3 coordinates. So instead of x, y, z, we're using r, theta, phi. Anyway, the Laplacian is just like the derivative in 3 dimensions for this, and it's, again, for some reasons that I'm not going to get into, but that are a little bit, they're a little bit interesting. It's not just like d dx plus squared, d squared dx squared plus dy squared plus, it's the Laplacian we found when we did the 3D quantum well was really nice because we put it in x, y, and z, and they all sort of separated into their own things. And welcome. But the Laplacian in spherical coordinates it doesn't separate into r, theta, phi. I can give you one quick reason why you know that can't be true is because dr squared, this derivative has an r on the bottom, that means it has units of like 1 over length squared. But if you tried to write d theta squared, theta has no units of length, so you can't add things that have different units. So in fact, there's a 1 over r squared here. So the units match. But anyway, that's none of this is things you have to know. It's just that that's one of the reasons this is more complicated, is because these aren't all lengths. This is a length, and these are not lengths. Whereas in XYZ, they're all very symmetric. They're all lengths, and they're all So in fact, that's called the Cartesian coordinate system. Obviously, the Cartesian coordinate system is the only one where the coordinates separate like that. That's why it's so nice, because they're perpendicular everywhere. I mean, these are perpendicular too if you draw the vectors the right way. But anyway, so that's spherical coordinates. So when you solve the Schrodinger equation in spherical coordinates, you get that it does separate like the XYZ thing we had before with the quantum dots, but it actually doesn't separate in all three. It separates into R, and then theta phi have their own package. So you could write this phi, or psi, sorry, this is, I'm not writing anything here. This could be written like R of R, which is its own thing, times Y of theta phi. So this is like the distance part, and this is like the spherical shell part. So what do each? So instead of the XYZ one where we separate it into X times Y times Z, which they're separate functions and they have separate quantum numbers that are unrelated, and when you write them separately, you see that they're just all infinite square wells. So we can solve them just like that. In this case, we can't quite do it that way. We have to do it like this, but they don't even separate. It's not like, well, then it's just a square well in R either, because of all the mixing of the Laplacian stuff. So anyway, these things give you some coordinates things that you can, if you want, I can send you a thing on how to solve it. If you'd really like to know how you solve this. These are called spherical harmonics. Someone was at Charles maybe was asking about it. Charlie. I know his name from Blackboard, that's why
Charles.
it says Charles. Charlie, yes, was asking, or someone, I think it was him, was asking about them in class one time, and I said to Google spherical harmonics because maybe it was Sean. Anyway, whatever. So this is spherical harmonics are literally the definition of this term is solutions to the Laplacian of just theta and phi. Those are called spherical harmonics. You can kind of think of them as like what is a sine wave? A sine wave is a solution to the Laplacian equation, right? This differential equation on a string. So it's actually like a linear harmonic, right? You can kind of think of, because remember when we solved the number of times I'm going to say guitar string in this thing, but if you solve the guitar string for psi equals, I'll just write k squared psi. I forgot, maybe we used u before. But anyway, solving this type of equation for the string gave you solutions like psi equals sine of kx, right? These were, you could call these linear harmonics. This is a linear Laplacian. This is the solution to the same equation, basically, with just some factors. I mean, you could just put that in k. We do put that in k usually. Where this Laplacian is for the theta and phi coordinates, because you've separated out the r. So these are, you can call them linear harmonics, sines and cosines. Also, I should put cosine with a's and b's. So these I could call linear harmonics. I'm only calling them that to make an analogy that these are exactly the same things. They're solutions to the exact same equation, but they're for the spherical version. So you can kind of think, well, like, if you try to vibrate a string, it vibrates in a set of sine waves. That's the mode that it vibrates at, and things look like this. So what happens if you try to vibrate a sphere? That's a kind of a weird thing to, like, what does that mean exactly? But if you imagine, like, taking I guess a balloon, but like a balloon is like very firm. I'm just trying to imagine like some kind of sphere that's like like a water balloon. How about a water balloon? There we go. Take a water balloon and you like flick it. Obviously, it's going to be sort of asymmetrical in how you flick it. But if you imagine just it vibrating, it can vibrate in these weird. If you Google, that's why I wanted someone to Google, or if you want to see pictures, Google spherical harmonics and look on either Wikipedia or Wolfram Math World. There's animations. I don't know if there's animations on Wikipedia. Anyway, somewhere there's animations that show you what it looks like. I mean, it's analogous to just showing you a sine wave. Obviously, showing you a sine wave like oscillating is not very interesting. But if you see them on spherical coordinates, it looks like just a water balloon, like blue, blue, and there's all these modes. And the modes depend on two quantum numbers called L and M. So because we've separated the spherical Schrodinger equation to the R coordinate and the L and M spherical harmonics, we get that the quantum numbers, of course, are just going to be this comes with one quantum number. Oh yeah, is that moving?
Mhm.
Oh, yeah, that's a very high L or M spherical harmonic, because the simplest ones are like they just kind of go like this, like a jellyfish or whatever. But then some of the higher order ones look like, they have like each quadrant is kind of anyway. They're kind of weird looking. But also you could do it in 2 dimensions. Now we're completely off topic. But in 2 dimensions, you could also do it, and it's literally solving this equation, but on like a drum. Like literally imagine an actual like a musical instrument drum that has a sheet on it, and the sheet is like a circle. And if you hit it, how does it oscillate? Well, we know how strings work when you hit them, but how do you hit when you hit drums? Well, you can imagine it kind of goes up and down like this, or it kind of goes like this, or it kind of goes in quarters or whatever. Those are I forget what they're called. Not spherical harmonics because they're not in 3 dimensions, but they're a 2-dimensional version. So they're literally halfway between this and this. Planar harmonics, I guess. So literally, this is 3 dimensions. This is 1 dimension. A 2-dimensional version is identical. Yeah, that's a spherical harmonic. That's probably 0, 0, but yeah. And so anyway, they're labeled by 2 quantum numbers. Let's get back on topic, which is talking about the quantum numbers, because that's what you need to know, which are that they're labeled by L and M, and because of things that you could look up that have to do with the spherical harmonics, you would get the ranges of these, and this is the thing I talked about really quickly in the class and last time, I think, which is that L can go from 0 up to n minus 1, and M can go from minus L to 0, obviously, and then to plus L. And this is sometimes called ML, by the way. And the reason is because MS, which is called the spin quantum number, is plus or minus 1/2. So if you really want to be super specific, an electron actually has an extra little one, because it has, not only do you have to tell me the solution in terms of 3-dimensional space, so therefore there's 3 quantum numbers, but you also tell me this 4th dimension, which is like the dimension of the spin it has kind of thing. So this has nothing to do with the other ones. This is not from the Schrodinger equation at all. It's just a fact that you know about electrons. It's from the Dirac equation, if you want to know.
I feel like I remember this from organic.
Yeah, if you want it, yeah, this is, you could look up the Dirac equation, which tells you, it's kind of like the Schrodinger equation, but it tells you about fermions. Don't look it up, it's not worth it. It's not very interesting, but I mean, it's very influential. It's just not gonna give you, you're not gonna be able to like see something cool from it. Anyway, so that's the Dirac equation. So the point is that you have these 3 quantum numbers plus an extra one for an electron that tell you about the state that they're in. They have these ranges which come from the math. And now, the kind of interesting thing is that they're sort of like, of course, there's infinitely many states. We know there's infinitely many states because n can go up to infinity. There's no bounds on n. Right? If I said n can only go up to like 5 or something, then there would be only a finite number of electron states of an atom, right? Because if n can only be finite, well, these are only finite as well. But it just turns out that because n can be infinite, these, you can have an infinite number of sets, but so 1, 1, 0, 0 is the wave function of the first, this is with a 1s state. Well, I guess it would really be 1, 0, 0 plus or minus 1/2 maybe, I guess if you really want to write it. But this is the wave function. So we've been writing them like this or like this, and that seems very disconnected from the wave functions we've been writing for other things, but they're of course the exact same thing. It's just that these are very popular wave functions in the world. And so we don't usually write psi 1, 0, 0. And of course, you could write that R function times that spherical harmonic and write out the whole thing in coordinates that people do. I don't remember how to write it, and it's not, again, not very informative. That's why they give them these labels. And that's also why, how do you get all these weird shapes? Well, it's from the spherical harmonics. That's where they're from. But this is called the 1s, and then what if we wanted to do 1? And now we can't do like, I can't just pick first of all, n, I should write, n can be 1 or higher. It cannot be 0. You can kind of see what, if you put in 0 here, you don't know what that means. So the next one you could have is, well, you can't put like 1, 2. We know we can't have a 2 here because L can only go up to n minus 1. So actually we can't even have anything, like if we wanted to say what's another state with 1 in it, well, L can only be 0 in this case. That's the only number it can be. And then M can only be 0 as well because minus L and plus L are both 0. So this is the only state. There's no other state we could have. So that's why we don't have a 1p, right? And then 2s, well, if we write the first number as 2, then L can be 0, but then ML is forced to be 0. So this is the 2s, sorry. And then what else can we have? 2, and now we can definitely have a 1 here now, because 2 minus 1 is 1. And then L can be, well, because L can be minus 1, 0, or 1, we can have this one, we can have this one, and we can have this one. There should be like commas I should write between them, but I'm just going to write this. So this means like 1 and the number minus 1. Anyway, these 3 are the 3 up and down in the 2p state. So these are 2p, etc. And that's why there's more elements in each n value down here. It's of course, again, I'm not showing you anything like groundbreaking. You can kind of just see it from here. But as n increases, there's more L's, and then there's of course more M's to pick from. And if each of those sets, NLM, has 2 electrons associated with it, of course you're going to get more and more, bigger and bigger sort of blocks. As you can figure out, because I said it's infinite, it doesn't stop at F either. There's also, you can go up to, there's like G, they call it, or whatever. You're going to run the letters, but if you use just the regular numbers, you can see that there's infinitely many. It's just that in real chemistry and stuff, that you're never going to see an atom with 1,000 electrons around it. If you did, you could figure out what states it could have or whatever. But also, I think these letters are important to know because that's what's used in the language, but they don't come from anything. Like the name, the reason why they're called these is because there were people in like the 1800s that made them up. It was called like spectral, and I looked them up once and it was kind of cool, but I forgot. Maybe it's spectral and something and diffuse, and anyway, they just are fundamental maybe. I know they don't mean anything. Those names they made up, they literally didn't understand it, so they made up stupid names. But they're kind of cool. But that's the only reason they're used. So these aren't like it's not like the P and D come from like the math of anything. They're just names for the L values. Yeah. And the M values we don't really give names to because I don't know why, we just don't. So anyway, sorry, I should mention, the principal quantum number, why do I always forget what L is called? The something quantum number? Anyway, and M is called the magnetic quantum number, usually. Anyway, it doesn't matter. So, the spin quantum number, I think. No, that's the S. Okay, I forgot. Anyway, there have names, but it doesn't matter as long as you know these and the rules and stuff, that's fine. So that's basically all chapter 10, I think.
Yeah.
And chapter 10 also includes the box infinite square well, which we've talked about sort of to death. We've done, I'll run through my little, in chapter 9, we've done the infinite square well and the finite square well, which is like, we've done those many times. And then the chapter 11 is like kind of the newer stuff, which we've also talked about the bands.
Mm-hmm.
And as far as I can tell, that's, and then a few of the homework questions are about stripping electrons off of things in bands, which as long as we know about the work function, which I talked about at the end of last time, I believe that's sufficient for the, I'm just trying to reassure you about the quiz. As in, I don't think there's like a big thing that I haven't ever talked about that's going to be on the quiz. I mean, again, I haven't seen it, but I really don't think there's a huge like unit or something that we haven't talked about. What are you talking about? Semiconductor? Oh, we talked about semiconductors a little bit.
Yeah.
Anyway,
You had a whole thing on.
That's right.
Whole
So,
hour.
yes.
Yeah, about an hour. Yeah.
Yes.
Awesome.
Perfect.
It was awesome. Well, I don't
You
know.
liked it.
That was.
He
those
likes
were-
that.
Nominated for an
I like
Oscar.
this.
What's that?
Nominated for an Oscar.
Ah, yeah.
Best.
He likes that.
Documentary.
I like this. It's great.
Yeah. What were you gonna?
I was just wondering if we could go over 9.9 because I can't find. You said you'd put a PDF on the Blackboard, right?
Oh, what was 9.9?
So it's up there.
9.9 was the extra credit one from number.
Oh, that's on the last video.
The last.
Wait, was it on the last video?
You put a PDF online.
Oh, I did. It's on the Sci Foundations.
Yeah.
It should be kind of the only.
I
PDF.
looked under course material and assignments. I couldn't. Find
No,
it.
the Slack. Sorry.
Slack. Okay.
Yeah, sorry. Did I say Blackboard? I said I didn't.
Maybe I misheard.
No. I think I said something
Yeah.
different.
Alright. Well, oddly enough,
So this. Sorry, it's the Slack, and then it's the last. I think it was the last video. I think I spent about an hour on it. So you will be completely sick of it
I think I
if you.
all right. So going from that, homework problem for assignment 4, chapter 11. Sorry, chapter 9. It asks to go over problem 11, which is a continuation of the infinite square well. Could we go over that if we haven't already?
Yeah. Let me look at it.
The
So,
Schrodinger
yeah.
equation one.
Page 169.
Oh.
Number
You
11.
have to write.
Oh,
out
that's
the
right, that's
Schrodinger
right.
equation.
Oh yes. Yeah, I can talk about it. So I also I also talked about it in the last one. I'm not trying to like just tell you like no, you can just go. No, I do want to help, but
No, it's okay.
I also can't do justice to my previous self. But I will talk about that real quick, which is that those two problems are very so they're very similar, obviously, but they're also like the second one, which is the 11, is like much easier because if we just try to solve psi equals e, what was it, e psi? Sorry, why can't I remember this? E minus v naught, sorry, e minus v of x, psi of x. Okay, this is the Schrodinger equation, right? And this actually has the solution of x equals a e to the I kx plus b e to the minus I kx when x is, or when k is 2m e minus b of x, I guess. So this, yeah, this is like sort of always the solution. Like it's kind of like the guitar string, or we always have the same solution. And in the second one, because it's a free particle in all of those regions, we have this solution in regions 1 and 3, and then in region 2, I mean, really, it's actually going to be. Sorry, let me write this a little more precisely. And then 1, 3, and then side 2 is c e to the I L x plus d e to the minus I Lx, where L is radical 2m not. And that's it. So it's like literally, it's like almost couldn't be easier than, like, the other one is difficult, but this one is, it's literally just solving the Schrodinger equation, the regular Schrodinger equation, and writing this. As long as you remember this is the answer, you just have to write it twice. So once you have this answer, you have it in both cases. The only difference is the energy is different. So in this region has a higher energy. I mean, it doesn't really have a higher energy, but effectively it's like, if this is the energy here, E, then in here it's effectively like the energy is E plus V naught, if this is minus V naught, and this is 0. Right, and so the Schrodinger equation, it's still a free particle. So here this is a free particle. Free particle means V is 0. So the solution just looks like this, with K as that.
But what exactly happens?
Happens,
Well, no, it's the way the problem is worded. What
Yeah.
happens when a quantum particle is traveling from the left?
Ah.
With energy greater than E is greater than V naught.
yes, okay. What happens when it's traveling from the left is that this goes away.
Okay.
And this goes away. Because these are moving toward the right.
Okay.
Which is also known as coming from the left, I guess. So what happens is that it continues to the right, and in region 2, it has a different frequency. That's sort of it. There's not that much that happens, I guess. In the other problem, it's very different. The other one where the energy was very low, it's not a traveling particle. It's a bound state that's free inside and decays exponentially outside. So that was like the hard. And then matching the boundary conditions there was very hard, and that involved a bunch of math that I did in excruciating detail, far more than you would want to know. Having to do with the graphical solution. It's basically, I literally did what's in the PDF, but I sort of did it out. It's not interesting. But the point is that when you take the energy above 0, so this is 0 and this is minus V naught, if you take the energy above it, now we don't have to do any, it's not like it's bound into this well, it's actually like a bird.
So the particle is free?
It's free everywhere, yes.
And then when it gets to region 2, then it's bound in the infinitely deep well.
When it gets to what gets to 2?
When the electron gets to region 2, what exactly happens that's
It's still a free particle, but the frequency is now this value.
And because the frequency is greater than the energy of the particle is greater?
No, the energy's
Because
so the actual value of the energy stays the same, but because it's kind of like your potential energy is mgh, and let's say your potential energy is your height above here, and then you go over like a canyon. Well, now your potential energy is kind of like greater, but like of course you actually didn't gain any energy. It's just that now relative to the bottom, you have much more potential energy. So so the only thing that changes, like the equation looks identical, it is identical. The only thing that changes is that you change E to E plus V, because you're effectively over a higher well. But in terms of what happens, like what the particle does, it just is continuing to move to the right. It doesn't actually it doesn't have to stop. It doesn't tunnel, right? Because it's a free particle everywhere. The reason we know it's a free particle is because the solutions have I's in them, and you know that because this is a positive number and there's a minus sign here. So the solutions look like, so I'll write free is like of U. I'll just write it as U instead of psi, so we don't, just to make it sort of in a vacuum. Minus K squared U. This is free, and then bound, I'll say. We wouldn't normally call it bound in like classical physics, but in quantum mechanics, this is a bound state, is plus K squared U. And the reason is because the solutions to this one, the bound one, look like this. I'll say minus. I mean, it's plus and minus, of course, but so this is like a real exponential. It's a decay. The solutions to this one look like have i's in them, either the I kx. This is a sine wave. This one is like a decay. So the bound ones will go to 0 eventually. The free ones will not. That's sort of, I mean, again, I'm realizing when you say it a certain way, it's like, well, sure, but it's, so the important part is the sign of this. So because the energy was always greater than the potential everywhere, then this number is always positive. And if this number is always positive, the minus sign here goes here and you get this situation always. So in number 11, it's always this situation. Although k might be a different number, because here it's different than here. In region 2 is actually different than region 1. But it still looks just like this. There's still a minus sign here.
Okay.
And that comes from this minus sign, really, because
So,
this is a positive number.
so the answer is that nothing much really happens.
Nothing much happens except for it's not the same plane wave. Like, the plane wave is defined by this k, right? That's like the frequency or the wave number, whatever you want to call it. It changes in region 2 because it gets, has this v naught here. But then it goes back to normal in region 3. So, like, it still remains a plane wave, but it changes frequency. That's why I drew it. I drew it with a different amplitude. I don't know why. It doesn't have to have a different amplitude, but it should have a different. Sorry, I should really, to draw it more accurately. I mean, you could look it up if you really wanted to see an accurate one, but like, I'll draw it with like a higher frequency, and then it'll go back to. So it would be like this, and it's moving to the right. If you added the b to the minus I kx, that would be fine too. It just wouldn't be moving to the right anymore. It would just be everywhere, which would also be fine. You may be wondering, so this is now sort of a side note, kind of a side note. You may be wondering about, I made a big deal a while ago about how all states that you solve this would need to be normalizable, right? We couldn't have a state that was just 0 everywhere. Like the psi couldn't be 0 everywhere because then you couldn't normalize it. How can you normalize this? It's like an oscillating thing that goes on forever. And the answer is, you can't really. And this is sort of an exception.
Can you define normalize?
Yes. That's a good idea. Normalizable means that this quantity, psi squared dx from negative infinity to infinity, is 1. Or is like a number. Because if it's a number, you can just take the square root of that number and multiply psi by it, and it's fine. Because the reason is because if you just take psi that satisfies the Schrodinger equation and you multiply it by half, it'll still satisfy it because you're just multiplying both sides by half. So you can multiply this by any number and it will still satisfy the Schrodinger equation. So in other words, you can scale any wave function and it will still satisfy it, right? If I just, take 1/2, just put 1/2 here, 1/2 here. Second derivative, well, it's a constant, so it comes out, and then they just cancel. So the point is that if I take the integral and I get 5, okay, I'll just make this 1 over square root of 5, so that when I square it, I'll get 1. The only reason so you might think, well, so then what does this mean if it can be any number? Well, if this is 0, I can't, like if psi is literally 0 everywhere, then I take the integral psi squared and it's 0. I can't multiply by anything to give you give me 1, right? So if psi is literally like when we do the infinite square well, what about the wave function where psi is 0? Does that satisfy Schrodinger's equation? Actually, it does. If you plug in psi equals 0, you get 0 equals 0. So it works. But the reason we can't say it's a solution is because in quantum mechanics, all wave functions have to be normalizable, and the integral is going to be 0. And there's no number you can multiply it by they give you to get 1. So this statement, when it's 1, is called, you'd say that psi is normalized. And also the only other situation besides 0 that you don't want is if it's infinity. So if you get a wave function, like for example, when we did the bound version of this, if the energy was here, on the sides we knew that it had to decay on the sides, and the reason is because like over here, this is a e to the minus kx kind of thing, decay. But we also have a solution that has e to the plus kx. That's like whenever we have these types of solutions, we always get both. that looks like a positive exponential, but we know we can't have that because we can't have the wave function go to infinity on the right side, because then when we take the integral, we'll get infinity, and we also can't normalize infinities, right? So we know this part can't be here. So basically, equals number, I should say equals number, but not 0 or infinity. Of course, infinity is not actually a number, but you can get infinity from doing integrals, of course. Basically, I could just say not 0 or infinity. In this class, now in a quantum mechanics class, again, we're not in a quantum mechanics class because we're not spending months and months on this stuff. But in a quantum mechanics class, you'd be expected to, anytime you write a wave function for any problem ever, you have to normalize it. If you write the answer that it's not normalized, it is wrong. Yes?
Is it wrong from you're submitting your answer wrong, or is it just wrong as far as quantum mechanics is concerned?
It actually is wrong from quantum mechanics because this is technically called the probability. So if you don't integrate and you just take the sample, like a range, that would give you the probability of finding it in a certain range. And if you don't normalize wave functions, you get that probability isn't conserved. Meaning that if you put something in a box and you have a probability of 1 of seeing it in the box, and then later it has probability 5 of seeing it in the box, that doesn't make any sense, right? Because then you're like, so what happened? But could have been the same thing, you just forgot to normalize it. So it actually kind of is a real thing. It's not just like a stupid convention. It actually has a real meaning because you do interpret parts of this, not the whole integral, but parts of this as a probability, as a distribution of probability, essentially. So the probability of finding something everywhere has to be 1. Otherwise, what does it mean to have a probability, right? And if you integrate this plane wave over all of space, you'll get sort of, you can't even do the integral. It doesn't sort of really make sense. Actually, wait, no you can't. Hold on.
Keegan, are you uncertain?
I am uncertain, actually. Hold on a second. Actually, you can do it. Hold on, what am I talking about?
Are we about to win the Nobel Prize?
Maybe. No, probably not. But A times, and now, so this, I should say that psi, when I write psi with bars around it squared, this is actually psi star times psi. This is the complex conjugate, which means e to the minus ikx times, and then it's a again, e to the ikx. Oh, okay, sorry. I don't know why it was saying you can't normalize it. So this is 1, and this now integral of, oh, no, it's okay, sorry. You still can't do it. Okay, sorry. I knew that couldn't be that easy. You still can't do it because now we have what? The integral of a squared, a is a constant, times dx from negative infinity to infinity. What's the integral of dx from negative infinity to infinity? Like infinity, I guess? I don't know, like it's nothing, so you can't do it. Sorry, I was like, I knew that was, yeah. So this is not normalized, but that's okay. Why is it okay? Because otherwise you can't really have, if you really had to do it, like how it really works, you'd have to do things called Gaussian wave packets, and it would be like a whole thing, and we'd have to, it would not be fun. But how things, so you might, well, actually, that's a good question that I asked myself. How, that's a good question, Keegan. How do
Let me tell you
particles
more.
travel? Like, how do we talk about literally a particle moving to the right? Like, they say a particle moving to the right. We saw that we can't write this because we can't normalize it, right? We integral of dx is x, and you plug in infinity, So how does it actually work in real life? We get a thing called a Gaussian wave packet, which a wave packet just means like a wave function that's a free particle that's sort of bound to one place. So it's like e to the ix. It's like this times this function, a Gaussian, like a bell curve. So basically, you have a free particle, but it's only in this little region, such that when you plug it in, you get that it sort of just moves by itself. So that's how we think of real particles. And so this is not like a silly mathematical abstract thing. It's like, well, sometimes it works, sometimes the rules don't apply. Like, it's actually a real thing. It's just that I think he doesn't, this is how all quantum mechanics classes work. We don't want to do wave packets yet because it's just a really complicated, like you have to do e to the minus, like mu I don't even remember what a Gaussian is, but it's like it just adds a complication that doesn't actually affect the answer at all.
Okay.
So we consider particles as this thing, as opposed to wave packets that actually sort of trap the plane wave.
For the explore more, I'm gonna totally jump ship here.
Yes.
Oh.
Okay, so you can get back on it in a second. For the quantum well heterostructures thing, he's just talking about like lasers, right?
So what's the question exactly?
Number 7, where it's like
Yeah.
explore additional applications. All I can find.
Oh,
is
that was this, but that's a semiconductor. Can you?
All
Is there
I
things about lasers?
Yeah, all I see are lasers.
You can write about lasers. I don't know. I actually have no
I've
idea.
written about lasers.
Oh, because all I know about that is what's in the book, which is like the quantum gas, the two-dimensional quantum
Yeah,
gas.
no, all I'm seeing are like lasers where they decrease the work voltage and increase the number
Okay.
of like
Yeah, say that.
quantum tunneling, whatever.
Sure, whatever. Yeah.
Okay, sweet.
So
That's what I'm
Just
doing.
basically just Google it and write something
Okay,
about
that's
what
what
they
I
say.
did.
Yeah,
I cited my sources.
it's more for you.
Love that.
I don't think I'm gonna like
Read them.
really go harsh
Love that.
on the
Okay,
scientific.
you can jump back on your ship now.
no, it's okay. We can keep going.
No,
I
I'm
have
good.
There's
this-
plenty of
that.
lifeboats.
Okay,
Are there?
so let's see.
There's several more before the quiz. Yes, there's Wednesday and
But only so much that we can make given our working schedules.
true.
But all right, so we went over. Okay, so we went
Women
over-
and children first.
Everybody's a child. Let's be honest.
That's fair enough.
In this scenario. All right. Calculate the acceleration. Did we go over number 4 for chapter 11?
We
Uh,
went over.
I definitely talked
Yeah.
about all the problems.
Okay.
But what is it? And I'll see if I can say something quickly.
Well, I was
the
just wondering about
acceleration.
yes, the acceleration part. So
Oh
in
yeah,
this
that was
case-
a little.
Yeah, so
the
we're-
energy and then the velocity.
So the
Yes.
issue with this is, I could figure out, electrons going from band to band, but when it
Yeah.
comes to electrons or speed or how quickly they do it, I was under the impression that they just, hopped instantaneously. You know,
Yes.
like the documentary said,
Which one?
the one that he showed
Oh,
us
oh,
in the last
yeah,
half
yeah.
hour.
Yeah, so they do. So when they're talking about acceleration, they're talking about acceleration under an electric field, not between bands. They do actually hop between bands.
The one you
Well,
discredited immediately.
Yeah, I wasn't. God, that was awful. Anyway, no, that video was fine. He's never. Okay, let me clarify. He's never showed anything in class that I think is stupid. That I think is bad. It's just that they're from things that are bad. But I'm sure most people that watch those, that see that clip on YouTube don't know what it's from. Anyway, whatever. Because it doesn't matter what it's from. But anyway, this is what's meant by the acceleration.
Huh.
Mm-hmm.
You have a very odd outlook on study materials, don't you, Keegan? You've got what some
Oh,
people call
sorry.
the artichoke heart approach. People hate artichokes, but they like the artichoke heart.
Uh-huh.
So, from everything that's bad or god awful, there's just the one good thing.
Okay,
I don't know. It's an odd
that was a
thing,
stretch,
actually.
but yeah, no, I'll take it.
Fine, you'll take it. All right. So that's the formula for.
Yeah, so
electrons?
A is just F over M, of course. I should have written this first, right?
All right.
F over M. Force from an electric field on an electron is this. This is the electric field. Like I'm not gonna. This is literally the definition of electric field.
Okay.
I could keep writing things that are kind of silly, but silly meaning not very helpful, but they're very true. So electric field is defined as the force per unit charge from electric force. So I guess I'll write E here. So the definition of electric, let me say that more precisely. The definition of an electric field is the force per unit charge of an electric force, which sounds a little bit circular, but that's actually the definition. So that's F, and M is this thing that we've derived. We didn't derive it, but it's from class. Well, we kind of derived it. It's from the last class, where you kind of take if this is K, and this is E, and the band kind of has some curvature, you say that it's kind of like pushing something up a hill. If it's a really steep hill, it's kind of like it's heavy.
Yep.
And if it's a really shallow hill, it's very light. That's kind of like the mass.
So there are some diagrams where you see the that slope just mirrored across the x-axis. So like in
Like
instead of-
this?
yeah, like that.
Oh yeah.
So what determines if it's going what the shape of the parabola is going to be?
You have to. They have to tell you. You can't
Okay.
determine it. Well, sorry, that's not a good answer. What determines it in real life is the actual material. So silicon or whatever might have a just different band structure.
So which one is easier to? What are the properties of having a band like that and a band like the other one? Like what's the benefit?
Well, this one technically doesn't have a mass
Okay.
because if you push it a little bit, it just falls down. So there isn't sort of a mass here. This one does have a mass because imagine like this is sorry, what was your question?
So I understand that the two different parabolas
Yeah.
are material dependent.
Yeah.
Right. If I were to look and see a parabola like that,
Mhm.
right, like that one, what does that tell me about the material? Is it does it correspond to how conductive or
Oh,
insulating
yeah, I
it is?
see. So it does not tell you if it's an insulator or a conductor, because that you have to know how filled the bands are.
Okay.
Because every material could be if you just filled it to a different level, right? Because we talked about if you have a gap and you have something filled here and the Fermi level is right above this, it would take a bunch of energy to excite an electron, so it's an insulator, and we talked about that. So you don't know if you just know about the bands, you don't know how they're filled. You don't know about the Fermi energy, and you don't know about the conduction properties. But you do know if there was an electron in this band, how basically how it would respond under a force. Because if you give it a force, this is K, remember? So K is like P over H bar. So K is kind of like a momentum. Right? Or you could, I guess you think of it as a velocity too, kind of. And this is how much energy it has. So the relation between momentum and energy is P squared over 2m, which is also H bar squared K squared over 2m. And if you know E is a function of K, the second derivative would give you this by Taylor's theorem. So, in other words, if you know the mass basically tells you if you try to move it along a band, how hard is that?
Yeah.
And moving it sideways along a band is just like changing its momentum. So literally, if you imagine, now what does that mean? How hard is it to change something's momentum? How much energy does it cost you? It's literally what mass is. So that's what this m down here is.
Okay.
So if you know E, if you expand E around the origin in a Taylor expansion, around the bottom, then the first term you get is a constant. So this might be like E naught is a constant. So you get E is like E naught plus 1/2 d squared E dk squared times k minus k naught squared. If this, if this is a value of 0, you just get k squared. So what I'm writing here is literally a Taylor expansion.
So looking at that formula for what the acceleration is equal to,
Yeah.
I understand that negative V is just the charge of the electron,
Yes.
right? The epsilon is just the electric field, which is given in the problem.
Yeah.
The second derivative of E in terms of K, that's just
Yeah.
taking the second derivative of that formula you wrote up there, right?
No, that'd be taking the second derivative of this. This is just the definition of energy of a particle with a momentum k. This is how you get. Sorry, I should say this is how you get this equation, because m is here. Is how you solve for m.
But if energy isn't given to us as a formula,
So they to do this, if you had to use this, they have to give you the they have to give you in a problem where you needed to solve for a, they would have to give you the energy as a function of k,
okay.
which might look weird and it might have a thing that's not a polynomial, but of course you could always do a Taylor expansion.
I'm at a bit of a loss.
So in that problem, I remember that there's a table where they tell you what a is.
There is no
They tell you
table.
what M star con over MO is.
Sorry, that's right. They tell you what m is.
But
Yeah, I see.
table that you're looking
Yeah.
at, yeah.
So M star, and then I was saying that, yeah, thank you. That's
M star con
correct.
over.
MO.
over MO, and MO is the regular mass of the electron.
All right.
So you multiply like that number they give you by MO, and that gives
So,
you M
yeah.
star con, which is what you use for the equation.
So if everything's in the conduction band, which I'm assuming it is, because they say something about conduction, then you only use that conned one. The other ones with the parallel and perpendicular are, I think, for other bands when it's in like a two-dimensional whatever gas it's called, but electron gas. But this, of course, is unitless. This is a number. So to get it in terms of masses, you have to multiply it by m naught, which is just the mass of the electron, which is 1 point.
9.11 times 10 to the
that one
What's
kilograms. Yeah.
M star? What does M star cons mean?
That's
Not-
this. I wrote the formula wrong. That's literally this.
No, but what does the con stand for? The mass
Con-
of the conductor.
No, that means that you're in the conduction band. So if this is the conduction band, that just means the top band. Well, I mean, there's no top. They go on forever. But if the top band, meaning the one where there's only one electron, or it's partially filled. This is called the conduction band. This is the curvature, right? The second derivative of something, of a function is called the curvature. The curvature of this band is called M star cont of the conduction band. The curvature of a random band would just be called M star or whatever.
So M still stands for mass. Right?
Yes, it's a mass because the curvature of the reason we know that is because the curvature of the E versus K, this is just real kinematics. This is not quantum mechanics, this is not conduction. This is literally just definition of kinetic energy. The E versus K has a curvature proportional to M.
Okay.
So there's defining this to be the curvature. So instead of measuring the mass by using a scale, right? Because there's not gravity that we care about here, right? It's all, But instead of doing that, we just measure it. We define the mass as how much energy does it cost you to move something to a different momentum. And we know by kinematics that's related to the second derivative because you need to take two derivatives to get to, right, two derivatives of this. So this curvature of this, the second derivative, we call M star cont.
Okay. Okay, so by multiplying M star con by the mass of the electron, we end up with.
By multiplying the number by the mass of the electron, you
by
get M star
multiplying the
cont.
number by the mass
Yeah,
of the
yeah.
electron. We plug that in for M star cons.
Yes,
All right, and then in that case, we just
you would just do, minus. If you wanted to find A,
Yeah.
you would just do this over M star cont.
can we really just swap variables like that?
Which variable am I
You're
swapping?
not
F is
swapping
just the.
What is that?
You're not swapping anything.
Sorry, I should write F over M. This is just abstract. And here I should always be writing the actual force. This is just a force.
Okay.
Yeah, so I'm not really, it's not a, sorry.
Okay, yeah, no, I'm all set then. That makes sense.
Yeah, I should have specified. If this isn't a formula, it's a sort of result.
Okay.
Yeah, if it was a formula, you couldn't just flip things around, but it's,
Okay.
Yeah.
Yeah. It's okay.
so what I was saying about you need to know the function of E. You do, but apparently you don't, because they just tell you the answer. Like how I just said so I said before because I forgot what was in the book. But what I said before is that you need to know how E is a function of K. It turns out, really you only need to know the second derivative of that because that's the part here, and M star con is literally the second derivative. So they've already just done. They're just not even talking about the curvature, but that's what it's from. So anyway. Yeah, and then the perpendicular and parallel are just if you do the same thing, but instead of over K instead of for the conduction band, if you do it for another band, but you could even go in different directions, like if you have sort of a sandwich, is what they were talking about with the gallium and the aluminum, whatever. You have a sandwich of things where in the middle, things are sort of free, and in the ends, they're sort of trapped between them. Then trying to move an electron up or down would actually be hard, because you're sort of moving it into this bread of the sandwich. And if you move it sideways, it would be much easier. And so that's M star parallel and M star perpendicular. Those are like the effective resistance to moving it in different directions. But cond is the one that is most important because it's the one for the conduction band, which is the sort of the band that you're going to do anything in, like make a object that has electrical properties, whatever, that's going to be in the conducted band. So that's probably all you need to know about this type of thing for the quiz.
Okay.
Because, I mean, the hardest part is doing a Taylor expansion, which I'm sure you're not going to. Apparently, they just give you the M, which is kind of how it should be, because why should you have to do all this every time? Also, who knows that these have good equations anyway? I don't even, like, I'm writing a Taylor expansion is about derivatives. But what if this is like a crazy function that you don't know how to take the derivative of? Like, you know what I mean? Like, someone should just do it and write it down so you look it up.
Nice.
Engineering. That's my image of engineering. I don't mean that in a offensive way, but
I don't like fence.
but why do the thing if you could just look it up is the
Yeah.
Yep.
Okay.
Because there's only so many elements if you just write them all down. If you write M of all of them down, just one person has to do it. You don't all have to do it.
Yeah, only people that benefit.
Exactly. So yeah, and then what was the other thing that was new? Oh, the 2D gas or whatever, right?
Mm,
That was the only other thing that was new from last week.
Right.
And that's sort of just so over there real quick. That's like you take a sandwich of three. I'm gonna draw it poorly, but if you take a sandwich of two elements. This is 1, 2, and 1 again, such that 1 has a very big gap between its the highest occupied band and the conduction band, which is empty now. So these are insulators, and this is like a conductor kind of, or a semiconductor. This could also be a or they could all be semiconductors, but just with sort of different size gaps. If the middle one is comparatively conductive, then you can get that electrons are essentially trapped. It's like in this direction, it's an infinite square well or a finite square well, because to go this way, it would have to cross like a gap, like a bigger gap. So it would be like in the z dimension, it would be like like that. It's a sideways square well. But in the x and y, and this is in 3 dimensions, so in the x and y direction, it's like a flat a plane where the electrons can move around it freely. And they're just in these bands, so they don't. They have different masses, but they're free particles. They don't have. They're not in a potential, right? So you get what's called a 2D electron gas. So it's the same as this. It's the same things. That's why they write M perpendicular and M parallel. Those are for the electron gas type problems. But they're all, of course, true. They're just the same thing. It's just that that's the only time you need to know those, I guess.
Can you re-explain what a phonon is?
A phone, yes. Oh, yes. I forgot about that. That's a good one. That's actually, this is actually kind of, because it's kind of weird. So a phonon,
I know, I'm making your day.
this is, just the reason it's cool is because there's no, like, numerical questions about this. It's literally just, like, a kind of a weird thing you think about.
Mm-hmm.
But, because they draw these pictures and you just see them and you're like, okay, sure, whatever, that's what happens. But actually, let me draw it down. But sometimes you think about it and you're like, well, let me just, why am I, there we go. Now, this is energy again. These are bands. This is K. Now, if you were asking before, why are some of them like this and some of them are like this? I literally have absolutely no idea. I have no idea. I don't even really want to hear someone explain it to me. But, and actually, it's the reason it's important when you asked it is because what is the mass of a particle here in this band? It actually is not even defined because the second derivative is negative. So it has a negative mass. Yeah. So like, what does that mean?
Antimatter, yeah.
There you go. Yeah, it's antimatter. It's not actually. No, that's not true. But I just, for the video, I don't want anyone to. I mean, there are. Well, okay. I'm not going to start talking about quantum field theory, but because in quantum field theory, this is how you define the mass of a real particle, not like a funny little mass in a band, but in a real space. What is a mass? What's the definition? It's the curvature of the potential it's in. Anyway, whatever. So now let's say you want to go from here. So you have electrons all over here, and this is the conduction band, and this is the whatever highest filled band, whatever the Fermi levels here, whatever. Let's say you just want to jump one electron up to here. Okay, that's fine. Just costs you some energy. How do you do this? Like, how would you do it if someone said like an engineering problem? How do you get electrons from here to here? Well, if you know this is E1 and you know this is E2, that's the energy level of this point and this point. Then you would have, what would you do? Well, you'd probably shine a photon with energy E2 minus E1, right? If you shine a photon on this electron, or just at this material with energy E2 minus E1, you'll jump up to here, right? It'll absorb it and you'll jump. So that's fine. But what if, and you've seen the pictures in the book or on the slideshow and stuff, of you have this band, and then you pretend that's centered. Actually, I'll make it centered. You don't have to pretend. And then it's like this. Again, why do they look like this? No idea, but whatever. Now let's say you want to get an electron to go from here to here. You probably want it to go to the lowest one, so it's still in the band, but you don't have to use as much energy. What kind of photon do you need? Well, it's still just this much energy, so if this is E3 and this is E4, you still need to shine a photon with E4 minus E3, right? But the value of K that the electron had at the beginning, this axis is K, which is momentum, right? Right. Remember, momentum P, this is actual momentum, is h bar K. This is a constant, so K is like, it's called lattice momentum, but it's the same as momentum, it's just with a constant. You want the electron to go from a state where it had 0 momentum in the lattice, right? To a state where it has whatever this value is, K prime momentum, right? Well, that's not going to happen by itself, right? We know we can't jump to a higher energy level by itself because that violates conservation of energy. But we also have conservation of momentum. That's like a thing too. We just haven't talked about it in like 3 months, but it's a thing. Those are like the only two, really. Oh, angular momentum, I guess. But anyway, that's like the only other thing. This actually will violate conservation of momentum. We have to have some other object have a momentum in the other direction with momentum h bar K prime, right, to the, I guess it's a vector. So if the electron if the change in momentum of the electron in this state, we found the change in energy, it's this, that's fine, so we're done. But if the change in momentum is going to be minus K prime, it's minus, because it's on the left, let's just say. So now the electron is actually moving in the lattice to the left. Something has to happen to the right, and essentially it's kind of like if you imagine the lattice as like a, let's say, let's say you had like a chain of springs that really, let's say like a mattress, a bed. How come I can't? Is there a name for the thing with springs interlocking?
The box spring.
Springboard?
Spring?
Spring?
The
No.
box
No, but
spring.
the metal, like you take everything off.
Bed frame?
Bed frame? Maybe I have a really old bed. What is it? It's anyway, you know what I mean. It's like basically it's like a.
It's a box spring, isn't
Is that what it's called? I thought the box spring was the thing. It's encased though.
it? Yeah, it can be.
Oh, okay. Maybe it's a box spring, but it's just the thing that has like springs.
How old is your bed?
I guess my bed isn't like this, but I'm remembering in college, That's
Oh,
how the beds were.
Oh, I see what you're saying.
like it has springs like this.
Like a platform.
Instead
Yeah, it's like a platform with springs that's
Oh.
very, like it's not soft. It's not. You
Yeah.
can. Yeah, maybe you'll. And it's like a bunch of.
instead of your
Yeah. Well. Yeah, but
instead
it.
of slats, it's
Exactly. So in college, I went to the state school, so maybe they don't have nice beds.
I don't
schools,
think
but-
they do.
But imagine this surface. So there's a bunch of, and I'm just drawing dots, but there's not like a thing there. It's just like hooks. It's like a bunch of little springs with hooks. Imagine this is your lattice. Now in every problem we've ever done in this, it's in one dimension.
Mhm.
So it's like a chain.
Is this better?
Yeah, I guess it's just what's inside a box spring. Yeah, okay. It's what's inside a box spring. Sometimes it's exposed
Sometimes.
if they don't have enough money, I guess.
Yeah.
From New York State. But anyway. So it's like this, and this is a 2-dimensional version. Now, of course, you could also imagine a 3-dimensional version, but just pretend this is, we're going to think of the two-dimensional one now. Let's say you need a state that has a net momentum of like into the spring.
Mhm.
What does that mean? I don't really know. But just imagine that the whole thing is going to kind of like go, right? Now it's not, that doesn't mean that the momentum went away or something. It just sort of was dissipated in the entire lattice, right? But because it's a lattice, it's not going to like accelerate or anything. It's just going to kind of like absorb it in like a net fluctuation. And that, now in real life, that would, you could imagine it's so small that you wouldn't really notice or something.
Mhm.
And in this case, it would be a one-dimensional version. So you just had a chain, and you sort of gave it a slight, like you dropped like a tiny little like rock on it, and just sort of like went like that a little bit, and it got kind of dissipated in the whole thing. That object in quantum mechanics, you can't just have a random amount of momentum like we were talking about with. Remember we were talking about with the delta x delta k is like 2 pi. Remember this whole thing?
Oh yeah.
And remember how delta x delta p was h little a, regular h? This is the uncertainty principle, right?
Yeah.
This showed that you can't just have a random amount of delta x and a random amount of delta p. They come in like units in phase space, like blocks or whatever they call it. Anyway, they come in like blocks. That's the whole thing of quantum mechanics. That even momentum comes in blocks.
Mhm.
That's why we can't have a bunch of dots right next to each other. They have to be a little bit of a distance apart. Anyway, so because of that, even vibration can't be is sort of self-contained as its own little sort of block that can't be separated. So that little amount of momentum is called a phonon
Oh.
with an N. So a phonon is a unit of momentum.
So instead of like a packet of light, it's like a packet.
Exactly.
Of
It's
momentum.
literally exactly the same as how a photon is just a packet of light. It's, of course, these things are like it's not like, I feel like how the chapters sound, well, maybe how I've always thought it was explained to me is that like, well, a photon's a real thing.
Mhm.
It's like a thing that moves and has energy. And a photon is just a little word you make up for this. They're just as real as each other. This is just an amount of energy that's self-contained.
Mhm.
And you can't have half that much energy because of the rules of quantum mechanics. I mean, sometimes you can, it depends how much. But like, this has to be exactly the amount of energy to fill up this. This is just another thing. You can call it a particle, but it's just a little amount of momentum now. It still also has energy because it also has a effective mass and that kind of stuff too. So it does have energy too, but it's basically conserves the momentum.
Okay.
But the thing is, because it's distributed in a lattice, it's sort of considered as like you can consider the net vibration of the lattice as like an object, and that's called a phonon.
Okay.
It's a little hard to imagine with this real example because you would think it kind of dissipates, and this doesn't necessarily dissipate. It could just keep traveling and maybe be absorbed, just like a photon. This could be absorbed by something else. This could be absorbed by another electron that transitions the other way with exactly this much, just like a photon. It's
Okay.
exactly the same.
I was just about to ask, does it have to be like exactly a certain
It
amount?
does
just
have
like
to be
a
exactly,
photon
yeah.
is?
As far as I know,
Okay.
I don't know that much about phonons, but I'm pretty sure it has to be exact.
Okay. That makes a lot more sense.
It has to be exact to go to that energy level.
It's like
Yeah. Well, so in
mass.
this case, it emitted a phonon because it went from 0 to this. If you could imagine that this band like is over all of space. I mean, this is like a material. So you can imagine another electron is going from here to here.
Okay.
Then it would emit a photon and absorb a phonon.
So like.
So it
the-
could absorb the same one,
The
right?
photon got it to switch energy levels, and the phonon got it to switch
Right.
momentum level.
This is the
Or
photon's
shift
job,
Momentum.
and this is the phonon's job.
Thank you for that.
Okay, that makes a lot of sense.
Yeah, and of course this only works when this is k, right? In normal x space, like when we do the quantum mechanics problems where we have x over energy,
Yeah.
that doesn't mean anything because it's just x, right? But this is the special case because all these bands are in momentum space.
Thank you.
Okay.
So this is all still in this sort of weird abstract world where points on this are actually wave functions like this. Remember the Bloch's theorem and how there's this weird plane wave times the periodic thing? That's why we're in this K space. So it's still a little abstract. It's not like the wave function here, we could draw it as E versus X like we usually do, but then it would just be an infinite periodic function, which you can't really draw anything of. And also, like you just couldn't see anything from it. So you have to label them by their K. So that's why we're plotting it over K. Because all the states of an electron in a periodic lattice, like a material, like a metal or like a whatever, are labeled by not their value over all space. Because their value over all space is sort of boring. It's not very. I mean, it has a value over all space, of course, but it just goes up and down and does something stupid. What identifies the states is the K value. That tells you what the different states could be. And that's what we're plotting. So each point on here is a possible value of K such that this is the wave function. So we're still solving Schrödinger's equation. We're just looking at one little tiny aspect because that turns out to be, when you solve it, the only sort of quantum number that you get.
Cool.
So this is the quantum number now, as opposed to before when the quantum number wasn't in the plot at all and we just had you just draw lines and that's called the quantum numbers or whatever. But this is we're plotting the quantum numbers. So this is actually, anyway, I'll just stop there.
That's cool. Thanks.
This is probably the most abstract thing we're going to do. I don't totally even understand this in an intuitive way. I can draw these and you can say, oh, sure, it's E versus K, and K is that. None of those statements are false, and yet that's not super you're not oh yeah. You're okay, sure. But it's momentum, and I guess you have to conserve it. You get, So anyway, don't feel like everyone else this is obvious. It's not. The other things kind of, at some point, maybe click, like this infinite square well. You kind of get it once you see it enough times of solving the equation and finding the energy levels and the boundary conditions. At some point, you're all right, I get that there's n. I can't draw a random curve because I have to fix the n's at 0, so it has to be sine of n or whatever, pi x over L or something like that. So you kind of get, okay, well then, and then when you plug that back in, you see, oh, E can only be these values if you just literally plug in the equation for E. Plug in the Schrödinger equation and solve it for E after you have the solutions, you just get the E values, and those are the energies. So you kind of that sort of is a little more intuitive. I mean, again, it's quantum mechanics, but it's a little more intuitive. This is a little stranger. So if this is still a little fuzzy, that's okay. Okay, we have time.
Problem number 10 in chapter 10. So a metal has a work function of
Yes.
1.5 electron volts. Right. Apparently there's part A and no part B, so I assume it's just one part. Alright, a photon of
That's
wavelength lambda is equal to 550
You
nanometers.
make your own part B. Yes, I remember that there was. So remember, I think it was the first thing we learned in this whole year,
Yeah.
was that E. Maybe I don't remember it. E photon or something was or maybe it was last semester actually, but it was something minus the work function. E of. Oh, it was this. It was this. Of course, I'm sure they use different letters or whatever.
HF is. Oh.
Yes, this is
equal
HF.
to phi plus EK.
Yeah, so this was when you have an electron. So in this problem, I remember this problem. They tell you there's an electron at the Fermi level, E Fermi, and they tell you that there's a work function. And essentially the plot, and I don't remember the exact question, but that's okay because that's not gonna. We can do a marker now, because I kind of don't sort of want to know because. Again, I don't want to teach you how to do this exact problem. I want to teach you how to do any problem like this. So, so the work function is the energy between, this is 0 energy, and this is the Fermi level of the material. And if an electron is at the Fermi level, that means that if you just give it the work function amount of energy, it will be at 0 energy. And that's it. And if you gave it a photon with more than phi, it would just get phi energy plus however much more, and that much more energy would just be this kinetic energy. So when they say, I think they say, what's the
Max velocity it can have.
In the vacuum.
yeah for a given? They tell you the wavelength or something.
550
Okay.
nanometers.
So they tell you the wavelength, therefore you know e photon. Once you know phi because they tell you, right?
Mhm.
And so literally the fact that there's a formula doesn't matter at all. It just means that it takes the amount of the work function to go from E Fermi to sort of 0 in the vacuum. And then all the leftover energy is E electron, which is just this, or you could write it as P squared over 2m. Just energy, and therefore you could find the velocity either like that.
So when we were looking at the energy of an electron, we got a formula like h bar squared times something over 2m. H bar squared times c squared over, I think, yeah.
You mean this one?
Yeah, pi squared over 2m.
This one?
I think so, yeah. So
This is for in an infinite square well. This doesn't even have to be electron. It could be any particle, but it's in an infinite square well.
and since this electron's in a vacuum, it's just different rules.
Yes, exactly. Well, the energy is just given by the kinetic energy.
All right.
Yeah. In here, there's no kinetic energy. It's a trapped. So actually, when it was here, it was trapped because it was in the material, and it had energy E Fermi. But once it's out and it's in the vacuum and it's free, the kinetic energy is just all the energy is kinetic, and it's just 1/2 mv squared.
Okay.
Yeah, these are properties of the system, not the particles. Yeah.
Okay. This one right here. All right. On page 198. I'm sorry. Do you guys have a no? Okay. On page 198, question 11.3. I have it right here. So
Okay, this was not a homework one, right?
actually, it was. Yeah.
Oh, it was.
It was homework number. This is
No,
the
that
last
is
one.
homework.
no, the
but
last
it's
homework.
assignment.
Yeah, I
Yeah.
see.
So it's
Oh,
talking
yes,
about-
yes. I remember this one.
So how many electrons could fit in the lowest energy bands in figure 11.5? This was a little bit confusing because as far as I
Yes.
can see, there's only one energy band.
Yes. Well, there's two. I mean, these are both bands.
Okay. So
But the answer should be the same.
okay, yeah, that's what I figured. So if this is the case, how many electrons could fit into the second band? So how many could fit into the second band? It would be the same thing
Yes.
because the formula involving this doesn't have anything related to what the number of bands are.
Exactly. Right.
Okay.
It doesn't say like there's no band. Yeah.
Another one that kind of drove me a little nuts. Why wasn't this just simplified to kf over pi?
Oh, they could. So to be honest, I don't know where the 2 in that equation comes from. The first 2 I understand.
Yeah, it's, this one?
The first 2 is from that there's 2 electrons per state.
Yeah.
The
And then the 2 pi in the denominator is the length of the linear K space, right?
yes, because that's the distance between those 2.
Okay. Is it always 2 pi?
Yeah, they define it to be 2 pi.
All right. And it says, okay, what is the Fermi wave vector Kf? I assume they were just asking for the definition, but then it says, what Fermi momentum does this correspond to? I didn't know there was more than one type of Fermi momentum.
What Fermi momentum does this? See again. Oh. Oh, I see. So they're just saying. So they're giving you n. Wait, NL is
Number of electrons.
for unit length. Okay, so N here, let me write this. So NL is number of electrons N. Electrons per
Volume.
unit length, which is going to be A,
Okay.
right? And this is what 2 times 2 kf over 2 pi or something.
Mhm.
They're telling you what n is now. They're saying if we have this many electrons, yeah, I think they tell you just the total number of electrons,
They do.
and they want you to find what kf is. So that's it.
Yeah, but then it says, what Fermi momentum does Kf correspond to?
Oh,
Can
I
we just
mean-
say Fermi momentum is Fermi momentum?
Yeah, and the only thing they could mean is this. Because, so every momentum P you could write as h bar k.
Okay.
Now, I guess you could write it like, I mean, so therefore you could multiply it by h bar. I don't know why. I think k is much more. Yeah, don't even answer that. Just, I mean, you've already done the homework, but don't even like.
Okay, it's not a, it's
Just
not a
K.
good question.
Yeah, I don't know quite what that means.
Yeah, you and me both.
Yeah. So I would say k is the Fermi momentum.
Ryan, you got anything?
No, I'm good. I'm sorry, dude.
Alright.
Oh, sorry.
Alright, we got 20 minutes. Going from there. We did that. We did that. I'm gonna have so many questions for you tomorrow after class. It's not even gonna be funny. Alright. Would it be I know you've done this already, but there are a couple of notes I just want to go over for problem 9.9.
Sure. Well,
Just a couple of points. You don't have to go over the
no.
exact thing.
What that was the finite square well.
The finite square well.
Yeah.
Alright. So, when we were looking at the finite square well, you mentioned basically it was asking us to try to find 3 different formulas describing it. Let's see.
In 3 regions.
In 3
Yeah,
regions.
yeah.
Let's see. There we go. Okay, find the first 3 wave functions, 2 even and 1 odd, and energy levels inside. So looking at looking at the document that you gave us, I'm having a bit of a hard time trying to figure out. I get that there are 2 different equations. You could say that there are 3 different equations if you note that region 1 and region 3 are right there.
Yeah. Okay. So sorry. This is a slightly different thing than what I was thinking about. When they say the first 3 wave functions,
2 even and 1 odd.
they just mean that in region 2. So if let's say this is the energy, and this is V naught, then when you solve the Schrodinger equation, you'll get that it's a free particle because E is above V naught, or sorry, this is minus V naught. It's a free particle, and the solutions look like sine kx plus b cosine kx. And then the lowest one, because, and I don't exactly know how they expect you to do it without solving it, but if the lowest one looks like they all have these decaying exponentials here because the energy is below the potential. So there are decaying exponentials. In here, the lowest state is going to be like this. It's going to be a cosine. Well, it depends where you put your A and B or whatever, or your 0 and A. But in the second one is going to be the next excited state, which is going to be like that. And the third one's going to be the third excited state, which is just that. It's literally exactly the same as the guitar string, which is the harmonics. The lowest one is n equals 1, then n equals 2, then n equals 3. Actually, sorry. Well, okay, I'll leave it like that. And the reason that now you get that one of them looks like this is even. One of them looks like this, which is odd. And then one of them looks like this, which is even.
Okay.
Those are the first 3.
So how do we get? I can understand how we have 1 even and 1 odd using that A sine kx formula.
Yeah.
How would we get the third even one?
That would be, so this is where you'd have to use so this is the formula, right? This is where you'd have to use the boundary conditions for here and here. Do they say show that
It just says to find them. That's it. And then after that, it talks about solving the transcendental equation, but Professor Z said that was extra credit.
Yes.
All right. And I'm guessing that comparing our results with the case for an infinite square well is also extra credit?
Yeah, that's all done in the PDF, but then also explained in the last video.
Yeah. Yeah, but finding the first 3 equations, I just can't wrap my head around the 1 even and the 1 odd and then the extra odd equation.
2 even and 1 odd. Not 2 odd and 1 even.
I'm sorry, 2 even.
Yes.
Just I didn't know if that was what was confusing you, and I thought I solved the problem.
Well, it actually, so it depends on where you put your. So actually, so what's bothering me a little bit is how you're supposed to know that without solving it, because they specifically don't want you to solve it, right? I don't think you can even. Well.
You say a good bit of work.
I don't think you can actually know that.
See you guys tomorrow.
Yeah. This question bothered me a little bit before because until you solve it, you can't really know that some are even and some are odd. The thing you can know is that because it's a free particle, the solutions look like this. All of these, no matter what this is, these are all odd. And all of these are even. Right? Cosine is always even, sine is always odd. Now, until you solve the boundary conditions, you don't know the lowest energy states. So I'm not sure. If in the infinite square well, you can actually solve it, because we have before. And you would get that the lowest one is, so, okay, so I think that's impossible.
So can I just put on the problem that the question is impossible?
Well, you could put that it should match the infinite square well, roughly, in some limit, but you should match this. This one you can definitely solve psi, because the boundary conditions are just 0, right? The, psi has to be psi at, if this is 0 and this is a, then psi at 0 equals psi at a, which is 0, and then you will literally get sine and cosine. Sorry, no, you will literally get sine. You will get sine of n pi x over a. This is literally the answer.
That's the third even equation? Sorry, that's the second even equation?
This is,
So yeah, it says to just try to find the 3 wavelength equations.
Sorry,
One
yes.
odd, and then another even.
You're right, sorry. I did that slightly wrong.
That's okay.
It should go from minus a to a, because then it's centered around 0. Because otherwise it doesn't really make sense to talk about even and odd if it's not centered around 0.
Okay.
So this is going to be psi at minus a equals 0 equals psi at a, and so I have sine of k of minus ka equals 0. This is the same as minus sine of ka equals 0, but actually that's the same as this. Plug in a, you'll get the same thing with a not a minus sign. So therefore we get ka equals n pi. This one is 0, and then you'll get k equals n pi over a. Oh, sorry. Nope. Because we have cosine. Sorry. Plus cosine of minus ka equals 0. And this one is going to be sine of ka plus cosine of ka equals 0. Now, sine of a negative number is minus sine of that number. Cosine of a negative number is just cosine of that number. So you get these two, if you subtract them, right? You do, let's do this minus this, you'll get 2 sine ka equals 0, and you'll actually, okay, you do get the same thing, n pi. So k is n pi over a, and then now your solutions are psi is a sine,
Okay.
and yeah, right, but we know k
Yeah,
now.
okay.
Yeah, over a plus b cosine n pi x over a.
So then we go ahead and we take first derivative, then second derivative to get the first even and then the first odd equation, right?
I think if we plug in n equals 1, I mean, what am I doing? Oh, sorry, there's, Well, that's okay. There's B's and A's. Oh, that won't change anything. Hmm. I'm a little confused. Somehow, because if n equals 1, I mean, so these are neither even nor odd. I think I'm doing something wrong. I don't know what it is. Sorry, I'll send you a PDF. How about that?
Let me take a look at something. So a little while ago, me and a couple of buddies, let me just pull it up. So this was the approach that we took. Where we tried figuring out what the first two equations could be given, let's see, this was from, there we go. We tried to figure out what the first two equations could be, right? So this was what we determined to be the first even. This was the first odd.
Yeah.
All right, and then after that, we got the third one here somewhere. Oh, sorry, this was the first even, this was the first odd, this was the second even equation. If we took those, would that fit the bill?
No, it should be, okay, it should be this, which is, I mean, this. It should just be these three.
Those three? Alright,
I mean,
so then how is it they don't fit?
well,
Does one somehow equal 0?
well, these are in, okay, well, oh, okay, sorry. I'm doing them in, I switched to this. Why I did that, I don't remember. This is really weird. This is, so these are from 0 to A. Oh, wait. Oh, okay. So the reason is here, the length is 2A. So this is actually not the same as this with n equals 1. So it should be, okay. So you can either do it like this, where this is 0 and this is A, or you can do it where this is minus A and this is A, which is this.
Okay.
If you do it with this, this is the answer.
Okay.
And it's not obvious to see that this is even or odd right away. But A is actually half of the length of the thing. So it's not as clear as it's not as clear as this is an odd function, this is an even function.
Okay.
Right? That would be normally, but it's not as clear. The reason is because this is not the length of the cavity. If you do it like this, you'll only get sines.
Mhm.
Yes, you will only get sines, and then it will just be one function that would just be like this, and that's it. And then it's not actually centered around 0, which is a little weird, but you should be able to see that this is an odd function, even though this looks like they all look odd because they're sines. They're not centered at 0, so we can't use the sine cosine rule, but we can just see that this is symmetric, and this is anti-symmetric. And that's literally what odd and even mean.
Okay, so assuming that's negative A to A,
Yeah.
then those three signs, from 0 to A, those three signs are the correct answer.
From 0 to A, these are
Okay. And 0 to A.
and
is
from
correct.
minus A to A, these are correct. I mean, you could even just divide this by 2, and then you'd get a 2 up here.
All right. So in this case, it is negative L to L for question 9.9. So in that case,
Oh yeah, so then it would be and then you just plug in n equals 1, n equals 2, and n equals 3.
and then we're done.
And that's it. And they're going to look weird. I mean, you can plot them, and they'll look normal, but they'll look the same as this. But if you just
So it's just going to be the first even is going to be A sine pi x over A plus B cosine pi x over A.
yes,
A sine 2 pi x over A plus B cosine 2 pi x over A, and so on.
yes,
All right. And that's the correct answer.
yes.
Okay.
I don't see why that wouldn't be right.
I'm sure we'll find out.
I will let you know
Okay.
if tomorrow morning I wake up and realize that this is completely wrong. I
Okay.
will message you and everyone like a correct solution. But I believe this is correct. Something is not sitting right because I feel like I haven't written this before, and I feel like I would have written this, so I don't know why I haven't written this before, but maybe no one's
Maybe you
asked.
could check that against your. Maybe you could
I'll
check
check
that
it in the
against
book.
your old video from
Yes.
last. See if maybe you were answering a different question.
Yeah,
You
'Cause I
tried to
definitely-
answer, you tried to answer question 9, but you ended up going a different direction, or maybe
yes.
you did solve question 9, and this is just you going in a different direction.
Yeah. Yeah, what did I do? I don't know.
What did you do?
I don't even remember.
I tried looking at the PDF too, and I was just looking at that, and I was thinking, what the frick?
The PDF is a solution to that one.
Yeah.
But it's an exact solution. It's not like describe the first solution where it's literally an exact, they match all the boundary conditions.
Yeah.
And the only reason I showed everyone that is because it's just sort of good, I guess, practice to see like the full details of a calculation, but it's not super like you won't have to do it on the on a quiz. I doubt that would be very mean.
Is the thing still running?
Good. I will stop it now.
Yeah, thanks for sticking around so long. I appreciate it.
No, it's not.